So, are you okay? I think Tarcísio is already recording, so I'll start to make an introduction. It's our great pleasure to welcome Dr. Diego Rubiera Garcia to the YouTube channel of the Mário Chamber Gravitation Group, Federal University of Pará. Dr. Rubiera Garcia is a theoretical physicist and a faculty member in the Department of Theoretical Physics at the Complutense University of Madrid, Spain. He is internationally recognized for his outstanding contributions to the gravitational physics, general relativity, and black hole research. After completing his PhD in theoretical physics, he carried out postdoctoral research in Portugal, Brazil, France, and China, establishing an extensive international scientific collaboration network. Dr. Rubiera Garcia is an associate member of the LISA Scientific Group. He is also a member of the Einstein Telescope Observational Science Board. In addition, a member of several international scientific societies, including the International Society of General Relativity and Gravitation, the Spanish Society for Gravitation and Relativity, the Portuguese Society for Relativity and Gravitation, the Italian for General Relativity and Gravitation. Research focus on some of the fascinating topics in theoretical physics, including black holes, wormholes, modified fields of gravity, compact objects, cosmology, gravitational waves, black hole shadows, and possible observational signatures of quantum gravity. Throughout his scientific career, Dr. Rubier published peer-reviewed scientific papers. According to Google Scholar, his work has more than 8,929 citations, and he has an H index of 47 across the national research. Today, Dr. Rubiera Garcia selected The Secret Life of Black Hole. Dr. Diego, it's a great honor to welcome you to the Mountain Gravitation. We sincerely thank you for accepting our invitation and for sharing your knowledge and enthusiasm for science with all audience. The stage is yours.
Então, obrigado, Enrique. Eu fico muito agradecido pelo convite para falar deste tópico. So I'm very grateful for your kind invitation to talk about this topic, which I hope will be interesting to people listening to it. So it should last for 50 minutes, in which I'm going to tell you a little bit about black holes, which is a fascinating topic. Because not only black holes are fascinating entities, they are also real, according to the evidence we have been collecting in the last decades. And so I'm going to tell you different aspects of black holes in as a non-specialist way as possible, just talking about the sense, about what do we know about black holes, and particularly about their secret life, because they are as interesting objects as difficult to get access to them. So we are going to revolve about both theoretical aspects of black holes, but also about the different evidence we have about their existence within different channels. So this is the talk is the secret life of black holes and how we are peering into this secret life along the years, a process that has been speeding in the last few years. Okay, so where do we start from? So black holes are real. We are pretty sure that this is true, 100% confidence level, as we will say. But there is always the possibility that we are wrong, because this is science and we need to doubt about everything, including those things that we are most secure about or most certain about. But we have been gathering plenty of evidence from different sources, from the old-fashioned X-ray emission, which is a technique dating at least 50 years ago. But in the last decade, we have got access to these objects via two different additional channels. On the one hand, gravitational waves. So this was a discovery in 2015-16, so 10 years ago. And then the so-called shadows, or the imaging of these objects, which dates back from the 2019 and 2022. Okay, so these different pieces of evidence upon the same object, the black hole, so has triggered the awakening of a new era in strong field astrophysics that we call it multi-messenger astronomy, which is doing astronomy with different carriers, from neutrinos to cosmic rays to gravitational waves and to the old-fashioned but still very effective electromagnetic radiation. So we are at some kind of, let's say, revolution in our understanding or observational understanding of these objects, which actually these objects have been around us, among us, for a very long time. So they were proposed even in a naive way already back in the 18th century by a paper sent to the Royal Society in 1783 by John Michell, in which he conjectured about the existence of objects that are so massive that the escape velocity from them is at the speed of light. Now, the escape velocity is something that we have an intuition. Everybody of us has an intuition about them, because every time you throw a stone up to the sky, so after some time the stone will stop moving and then fall back to Earth. So if you increase the strength, the force you apply to this stone up, then the highest altitude you will get. Now, supposedly, if you apply a force strong enough, then the stone will escape from the gravitational field of Earth towards deep space. So the borderline velocity that you need to set upon the stone in order to run away from the Earth is the escape velocity. Now, this escape velocity depends essentially on the mass and the size of the object. So it will be greater in Jupiter than in Earth, and it will be greater in Sun than Jupiter. Okay, so theoretically, it could be that there exists objects in the universe in which the escape velocity is so large that actually gets to the speed of light. So such an object, in such an object, the light will not be able to escape to get to us. So the object will appear as completely dark to us. So namely a black hole, even though the word of black hole was coined much more later in time. Now, the actual framework in which black holes take their full meaning is general relativity. Okay, so this is the theory proposed by Albert Einstein in 2015 in this paper, and which provides the basic framework in which every cosmological astrophysical phenomena happening in the universe is framed. Okay, it makes sense every of these phenomena. Now, general relativity contains a lot of interesting things, but today we are talking about a black hole. Now, how we can make conceptualize, make a clear idea what a black hole is, because we were talking about escape velocity, but this is a Newtonian concept. In general relativity, we have to generalize this idea to escape velocity to something which is called the trapped surfaces and horizons. Now, to understand what is this, so there is an analogy we can follow. Imagine that you are observing a waterfall, and due to ill luck, you fall into the waterfall. So the water tries to drag you away to fall down into the waterfall, the bottom of the waterfall. And you want to avoid this, of course. So what you try to do is to swim back against the current in order not to be dragged by the waterfall to the bottom and then die there. So then you need to swim fast enough in order to avoid this dragging effect to take you to the bottom. Now, how fast you need to swim? So fast enough in order to overcome the velocity of the current. Okay. If you cannot swim fast enough, then you will get to the bottom of the waterfall. Okay. So if you are swimming slower than the speed of the water, then you are trapped in the water, and then your fate is already sealed. You will be died. You will be killed. Okay. So then, when you are trapped in the waterfall, no matter how fast you can swim, then you are within a horizon, because if someone tries to rescue you from the waterfall, then this person needs to get to you and then try to swim back. But because then both of you will be trapped, and then the fate of each of you will be sealed. You will get to the bottom of the waterfall. So a trap surface, in this sense, is a region of the waterfall in which, no matter how fast you can swim, then you cannot escape from the waterfall. You will be trapped into it. Okay. A black hole is an object that has a trap surface, a region around it in which you cannot escape from it. So now, this is what the property that defines a black hole. But actually, a black hole is a much more complicated object because it has different features that characterize them. So we can talk about the anatomy of a black hole. Now, this picture depicts the 5 most relevant surfaces that you can find, or the 5 most relevant elements that you need to have in mind in order to clearly understand what these objects do and what these objects does. So we are going to review each of these properties that you have here one by one. Okay, and this is a picture depicting how exactly each of these features of the black hole work. Now, first of all, black holes have no hair. This is the actual statement of a paper in which this property of black holes was unveiled. And it translated to common terms means that a black hole is described using 3 and only 3 parameters, namely the mass, the electric charge, and the angular momentum, or in other words, the speed. Now, this is something that makes no sense at all, because every other physical system that we have in nature, in order to be described, typically requires a very large number of parameters. For instance, suppose that you try to describe what is happening in the room in which you are at the moment. You need to describe every single object that you have there, physical object, from your table, your chair, your computer, everything, which is an aggregate of a massive number of particles. Each of these particles are doing different things. So you need to prescribe which of these particles are doing. And not only that, you need to prescribe the chemical and mechanical forces that are acting upon each of these particles. And not only the physical objects, also the air, the water, everything that that you have in your room requires an extremely large number of parameters to be described properly. Now, in black holes, this is not true. You only need 3 parameters, meaning that every other black hole in the universe having the same mass, electric charge, and spin is exactly equal to every other black hole that has the same parameter, which is the different situation that you have in your room. Your room is completely unique in the entire universe. There will be no other room like yours, with the same number of objects, same number of particles, the same number of features and properties and forces. Nothing. There is no 2 completely equal existence in the universe. But in black holes, this is not true. Okay, as long as they have these 3 parameters being the same, the black hole is completely indistinguishable one from another. Okay, so it's one of the simplest, perhaps the simplest objects in the entire universe we know about. So meaning that everything that you throw into the black hole and crosses the event horizon, no information is retained about them. Only the mass, electric charge, and angular momentum of the object that came to here can be recovered, and only in a collective way. Everything together cannot be separated. The contribution of the mass of this radio and the breadth is the same. It's only matters the mass and the electric charge and the speed. Now, the second property that we already talked about is the event horizon. So this is the surface. It's not a surface because there is nothing, no physical barrier there. It's kind of frontier that separates what happens inside the black hole against what happens outside the black hole. Okay, so once you cross the event horizon, you cannot escape from it. You are trapped in the black hole and you cannot run away. Not even light can run away. So it's one-way membrane frontier. Everything can cross the event horizon and explore the interior region, but once you cross the event horizon, you cannot get out. Okay, so it's one-way surface. Now, if the black hole rotates and every single black hole in the universe rotates, then there is another region, which is called the ergo region. The region lies beyond the event horizon, above of it, so accessible to external observers, is depicted here above the event horizon by this dashed curved line. An ergosphere is a surface of rotation in the sense that every observer that crosses the limit of the ergosphere, so meaning enters here, can still escape from the black hole. It can travel in some kind of trajectory like this, but while the observer is here, it is forced to co-rotate with the black hole. Meaning, if the black hole is rotating like this figure in this direction, from the bottom to the top, then if you cross the black hole, you also have to travel from bottom to the top. You cannot travel from top to the bottom, okay? But as I said, if you are here, your fate could be still cross the event horizon, never to come back, or you can run away. Okay, so this is the ergosphere, which is a different surface than the event horizon. Third property is photosphere. What is the photosphere? A black hole not only drags observers' particles light upon them in order to be swallowed after they cross the horizon. Okay, they also bend light trajectories in a very extreme way. So as a photon, as a light ray approaches the black hole, its trajectory is more bended as the closer they are. So this is a basic prediction of general relativity, which was experimentally verified a few years after the development of general relativity. Now, this effect is very extreme in the case of a black hole. Actually, it's so extreme that there is a surface which is different from the event horizon and different from the ergosphere, which is above the event horizon, above the ergosphere, in which the bending of light is so extreme that photons can complete one full circle about the black hole, or even more than one circle around it. Actually, formally, they can travel infinite times around them. This is called the photon sphere. It's a sphere of infinite light bending, in which a photon could circle the black hole indefinitely. And there is another feature related to this extreme bending of light, which is that the black hole, as seen by a faraway observer, you will have a dark central region inside it, which is not actually completely associated to the event horizon, because remember, from the event horizon, nothing can escape, so not even light. So this means that, at the event horizon, you cannot see anything running away from it. But it turns out that this shadow is larger than the event horizon, because a combination of different relativistic effects. So to summarize this, in a typical observation via electromagnetic radiation of a black hole, what you will see is a central dark region, which is called the shadow, surrounded by extremely bended light ray trajectories. Okay, so in particular, light rays coming from the sky, from all the stars in the sky that go to the black hole, will be extremely bent. So what you can find is that a photon that appears in some part of the photosphere can actually come from a star which is located in the opposite of the sky, because of this extreme bending of light. Okay. The fourth property of a black hole is the accretion disk and relativistic jets. So a black hole is typically surrounded by an accretion disk. An accretion disk is nothing more than the material that the black hole is trying to absorb, trying to swallow. But because the black hole is actually quite a tiny object from astrophysical standards, so matter cannot go directly to the black hole. Instead, it accumulates around the black hole, losing energy and angular momentum as time passes by, and eventually being swallowed by the horizon. While this process is happening, this aggregation of matter around the black hole it emits electromagnetic radiation and produces both accretion disk, and relativistic jet. The accretion disk is nothing more than the material that is accreted by the black hole that surrounds it, that is being heated up because of the different forces that act upon the system, and at the same time, a part of the particles that are being heated up will be expelled by the black hole in a perpendicular direction to the rotation plane of the accretion disk, as is depicted here. Okay, so here the accretion disk is in some plane, and the radiation is emitted perpendicularly. This is a relativistic jet, and it's a trademark, an observational trademark of the existence of a black hole. It's a canonical way of looking for black holes. For instance, in many galaxies, many centers of the galaxy, we observe the relativistic jets. And because this is a typical imprint of the existence of the black hole, it becomes a good spot in order to look for the actual existence of a black hole. Okay? So the fifth characteristic of a black hole is the singularity. This is the most theoretical one and the most mysterious one at the same time. Because the natural question, after what we have been talking about, is that since everything that crosses the event horizon cannot escape, this material has to go somewhere. So where does it go? So general relativity tells us that the final fate of this matter, no matter their properties or any other circumstances, they will get infinite time to the central singularity. Now, the singularity is something in which everything that could go wrong with the structure of the space-time does go wrong. So we cannot predict what will be the fate of an observer when you get to regions of the space-time so close to the center of the black hole, in which curvature grows without bound, and the trajectories of particles cannot longer be predicted. Okay. Now, this implies a loss of causal determinism. Determinism is the idea that, provided some initial conditions, meaning that I know where my body started this trip and how, after a given time has been elapsed, I can predict the exact location and velocity of this body. So I know every forces and every other things happening in the system. Now, the singularity challenges this determinism, and actually it breaks it down. Now, this is usually interpreted as a failure of the theory to predict, and also means that pushes the community to seek for improved versions of the gravitational field, or in other words, improved versions of general relativity. So this is in some sense, the existence of a black hole, which is a basic prediction of general relativity, is also the source of its doom, because general relativity predicts the existence of an object, which is the black hole, whose existence predicts the failure of general relativity. So in some way, the theory is telling to us that I'm incomplete. I need some better description of myself in order to describe what is happening in the innermost region of a black hole. This is called the singularity. Now, I didn't mention about the tidal forces, which is also another typical feature of not only of black holes, actually about any gravitational body, including our own planet, the Earth, which is called. So basically, this is what is behind the tidal, the motion of the sea in our planet, which is because there is a difference of force acting upon different parts of the body. So in this case, this is our observer or astronaut, which is falling into a black hole. So his feet, which are closer to the horizon, will feel a stronger force than his head, which is farther from the black hole. Okay? Because the black hole exerts a very strong force, which is larger here than there. So in some sense, your body is trying to get spaghettificated, in the sense that the pull upon your feet is larger than your head, so you are being pushed by the differential force. Now, this happens also for objects that are falling into a singularity. The closer they are, the stronger is the difference of force. So supposedly, every body will be destroyed even before getting to the singularity, which is also another cause or another motivation to stay in general relativity and to prevent the existence of these absolutely destructive forces. Okay, so now after we have seen the most important, most interesting aspects about the anatomy of a black hole, let us talk about taxonomy. Okay. So what kind of black holes are? How do black holes grow or come to exist? So we know, we are quite certain that we know about the existence of one process of formation of black holes. Okay, so this process has been built along decades and has been verified according to different observations. So we believe, or we are strongly convinced, that we know how black holes form out of the evolution of some types of stars. So every star, or most of the stars, are born out of the contraction of an initial gas cloud due to any kind of perturbation. Now, once the cloud gets a temperature high enough in order to ignite the fusion of the hydrogen on its inners, then the pressure exerted by this nuclear fusion will provide a counter force against the gravitational collapse that tries to push down the star. Okay, then an equilibrium is reached in which the gravitational pressure of the collapsing matter is exactly counterbalanced by the external pressure, the outwards pressure exerted by the nuclear fusion. Now, this is the main sequence of stars. Okay, so we can see it here. So while stars are in this sequence, so they are more or less a stable way, burning hydrogen and also partially helium and carbon or oxygen, depending on the kind of star, how massive it is. But no matter the particular details of how this fusion occurs, all of them are in this band, which is the main sequence, which relates the luminosity of the star against its color, which is an indirect measure of its temperature. Okay, so every stable star burning these light elements by nuclear fusion is located here. Now, when a star runs out of hydrogen, then it no longer can counteract the gravitational pressure. So the star contracts. And what happens then is that the temperature in the core increases. At some point, it starts the ignition of heavier elements, helium, carbon, oxygen, and so on. So this process produces extra life for the star, but it's much more short-lived. So it lasts for much less than the time that the star has been in the main sequence. And it cannot last forever. Why? Because heavier and heavier elements are being consumed by nuclear fusion. At some point, you get to iron, at which point the consumption, the fusion the nuclear fusion of iron doesn't produce energy, actually consumes energy, takes energy from the medium. At this stage, the star contracts again upon itself extremely fast, almost at the speed of light. Now, the exterior layers of the star collapse and eventually hit the nuclei of the star. But the nuclear is extremely robust, extremely hard. What happens there is that these external layers hit the internal nucleus of the star, and then it rebounds. It does rebounds as two balls hitting one another. Every sort of nuclear physics processes happen there. And the net outcome of the process is that an extremely huge release of energy occurs, mostly driven by neutrinos. Okay, in this process, the external layers are evicted out to space, and only part of the original nucleus remains. Now, depending on the mass of this nucleus that is left behind, now there is no internal mechanism known by physics that can sustain the gravitational collapse of this object, of the gravitational forces. And the nucleus contracts, and contracts until an even horizon is formed. In such a case, a black hole appears. So the explosion is called supernovae. Okay, is so like this one, which is a very famous picture, right? And because these are typically precursors of the existence of a black hole, not always, because many times a neutron star is formed instead. It depends on the mass of the original star. But this is a good place to look for black holes. Okay, so these are stellar mass black holes formed out of the collapse of stars. But there are other kinds of black holes we are aware of. This is the case of supermassive black holes. So now we know that there are supermassive black holes at the core of basically every galaxy in the universe. How do we know this? So we can check this in the case of our galaxy, the Milky Way. So when we look at we try to look at the inner part of our galaxy, which is not easy because it's quite opaque, so it's not transparent to most of the light. The X-ray emission managed to get out. So we see that there is something in the inside of our galaxy, in the inner part of our galaxy, which is extremely compact. Okay, and how do we know it is extremely compact? Because we cannot see the object in the middle, but we can track the motion of stars around it. So these stars, these trajectories that appear here, they are called the S stars. These stars are revolving around some central object at extremely fast velocities, very close to the object. Okay, but the central object cannot be seen. But we can estimate its mass just by tracking the motion of these stars. So this is actually mostly Newtonian physics. And we know that there must be some kind of objects of the order of 4 million solar masses. So it's the mass of our sun multiplied by 4 followed by 9 zeros. So extremely huge. But the object itself emits no light. So it's a natural place to look for a black hole. Okay, we don't know at the moment how these supermassive black holes came from. We have different theories, but none of them is consistent. We know they are there because we cannot see them, but we can feel its gravitational interaction. But we have no actual clues about where they came from. This is the opposite scenario of stellar mass black hole, in which we know where they come from. They come from the gravitational collapse of stars which are massive enough and that they have lost the capabilities to produce nuclear fusion. But in the case of supermassive black holes, we have no idea. Now, how do we know that there are supermassive black holes in galaxies? Because of what is called active galactic nuclei. Many galaxies emit extremely large relativistic jets, like this one, which is above around 5,000 light years of length from here to there. This is emitted from the innermost part of a galaxy, which is called N87, that will reappear later. Okay, so it's the same. So because relativistic jets, as we were talking about, they are frequently associated to the accretion disk that happens around black holes. So they are also a clear trademark of a black hole. This doesn't mean or doesn't provide a direct proof that this is a black hole, but it tells you where to look at. So every time you see a jet like this, look at the center with other messengers, with other mechanisms, with electromagnetic radiation, neutrinos, whatever, to see what is the nature of the object that is emitting this jet. Actually, black holes are pretty common in the universe. Not only stellar mass black holes, they are absolutely common. Okay, so there are thousands and thousands of black holes in our galaxy. And because black holes, they cannot decrease in size, we will see later that this is not strictly true, but it's very approximately true. So meaning that the black hole never stop growing. So there are animals that do the same thing, right? As long as they have enough food. For the food for a black hole is everything. For planets, stars, people, even light, everything contributes to a bigger mass of the black hole. And because the size of a black hole scales with the mass, this means that the more massive a black hole is, the larger it is too. So this is the biggest supermassive black hole known in the universe so far, which is above 40,000 millions of solar masses. As you can see here, so our entire solar system is here. And you can see how big the black hole is. In this picture, we also see the string bending of light around it because of what we were calling about the photon sphere and gravitational lensing around black holes. Now, we're pretty sure that these two categories of objects do exist. We will see more about this later. And there is something that has been conjectured, but we don't have evidence. These are primordial black holes. These are hypothetical black holes that were formed in the early universe out of primordial perturbation. And there are many theories that are at this respect, telling us that maybe they will have found mechanisms to grow during the evolution of the universe in order to still be around it. So if these objects do exist, we can look for them. Where do we look for them? Using two different ways. First, in particle accelerators, like the Large Hadron Collider in Switzerland. But also we can look them in the sky, because this process, these objects could also be generated of high energy cosmic rays. Now, it's fair to say that until today, we have no evidence at all about the existence of these black holes, and maybe we will never have. We don't know. But again, because we are scientists, we need to look for every possibility that exists in the book. Okay? So there are people looking for these objects, and we don't know if they exist, but maybe. So next stop. So we are going to hunt black holes. So I said several times that we know black holes are real, that we have evidence, but what is the quality of this evidence? How we can be so sure that they exist? Okay, so there are several ways to look at this. The oldest evidence we have about this is about their existence is not direct, it's indirect. What is this? So black holes cannot be seen directly because they emit no light. So we cannot only detect them about what is happening around them. So one way we can look at this is, okay, so most of black holes or most of the stellar systems are binaries. So they exist in pairs. What happens if one of the stars triggers its black hole phase? So it undergoes the supernovae phase and then converts into a black hole. So you have a black hole and another stellar companion. Now, because of the gravitational force exerted by the black hole, then it will get material from the companion. So this material will be surrounding the black hole. Okay. So you are looking for the electromagnetic radiation emitted from this black hole that at the same time has a companion. Okay. So the star cannot be seen. The black hole cannot be seen. The star can be, but the black hole does not. But we can use this combined observation in order to track what is the mass of this object. An object that we cannot see, so it cannot be a star. Because if it were a star, there will be means to see it. But we don't see it. But we know that it's there, because we are seeing its effect upon its companion. So this is strong evidence about the existence of a black hole. But it's indirect. We are not seeing it. We are only seeing what happened to its companion. Okay? There are dozens of candidates have been identified this way along the decades. But we are scientists. We like to doubt about the existence of things, but we also want to make sure that these things do exist. So in the indirect evidence is good, but it's not enough to claim that something exists. We want to go beyond this. So we go to gravitational waves, motivated by these systems. Someone, starting from the 70s until today, decided to go for the detection of gravitational waves. And why is this? Because I was saying you before that black hole, most of the stars exist in pairs. And there are also systems which are binaries that are made of black hole and a stellar object. But what will happen if there were a binary system made up of two black holes? So then it's a different situation, because it's not that the black hole is taking material from the stellar companion. No. It's that every black hole is trying to steal matter from the other black hole. Of course, they cannot, because nothing that is inside the black hole can get out. What happens instead is that they will try to approach each another because of the gravitational force until a point in which they will merge single black hole. Now, general relativity predicts that the outcome of this process will be the emission of the so-called gravitational waves. And this is a core prediction of general relativity because every object that orbitates in the universe and that has some motion emits gravitational waves. What happens is that this emission of gravitational waves is usually impossible to detect. But black holes are so extreme objects that in the final moments of this collapse to form a single black hole out of the two original ones, then the strength of the gravitational wave grows enough for detectors to find it. I mean, grow enough, it means that you have to detect an effect that is 1 part in 10 to the 20, raised to the 21st power. It is incredible to measure because every object, every other phenomena that you have in Earth produces a greater effect than that. So the main tool that we use in order to detect this effect is an interferometer. Interferometer is a very has been having different. The core idea is always the same. You have some kind of L-shaped structure like this one. You emit a laser source here. Half of the laser is transmitted to this test mass. Another part, the other half is transmitted orthogonally to this test mass. Then they come back from these test masses to the screen, and finally to the photodetector. Now, because these two arms that exactly the same length, this means that here, when light rays come back, they will recombine in order to produce a completely destructive pattern. So nothing will be detected in this photo. Now, suppose the gravitational waves entering through one of the arms. Now, gravitational waves are perturbations of the space and time. We will modify this distance that here very slightly, 1 part in 2021. But these detectors are divided in order to detect these tiny differences. Okay? So you will see one of the arms will see a transformation to its length, and the other one will see a different transformation of the length, meaning that the light rays this way and they will not travel exactly the same distance. And then when they recombine, the interference will not be completely destructed. So the photodetector will detect some remaining signal there. So this is exactly what LIGO-Virgo collaboration did. So this is a picture, okay, of the phenomena that we are trying to see. Okay, so there are two black holes that are orbiting one each another. So here there is a bigger one, here is a small one, okay, and then they are collapsing up to one another. So they are circling one another. So it's not one circling the other. Both of them are circling around some center of mass of the system, and the process goes on. It emits gravitational waves. Okay, so this signal is increasing, steadily increasing as the merger collapses. Okay, so here you see the amplitude and the frequency of the wave. Okay, so you see the amplitude here is growing very slowly because the two masses are getting close to each other. Okay, so the signal keeps progressing. See, it continually emits gravitational waves. So this is the signal, okay, that we observe actually. This is a real observation, these two hopes. And then they are getting to the final process of the merger, right? So this is the observed signal. This is what we are actually seeing. Okay? And then it keeps progressing, okay? And then it's frozen here. And let's see what happens here is that they finally merge here. They are going to merge, they're very close to merge, and plum. So then you have the gravitational wave. Okay, so this is the signal that you observe. As you get closer to the merger time, the amplitude, so the height of this wave is increasing. Okay, this is the observed signal, and this is the reconstruction then from numerical relativity. You see signal that is growing, and finally merger completed, then the wave flies away. Okay, So these are two different observatories that are using, they are not communicating to each another, okay? So, but they observed the same phenomena and got to the same conclusion. This is completely consistent with the merger event of two black holes of 29 and 32 solar masses combined, each of them, to produce a new black hole which are a smaller mass than the combined masses of the original black holes, and the remaining mass, which was of the order of 3 solar masses, was emitted under the phonogravitational waves. And now, this is really a direct proof the existence of a black hole, something that is happening right at the event horizon of the black hole, and there is no that the merger of two black holes. Okay, but now this was in 2015. Since then, there has been hundreds of detections that way. So these gravitational wave observations apply to stellar mass black holes that are born out of gravitational collapse. But we know that we also have another kind of black hole, which is the supermassive black holes that do exist as the center of most galaxies. So because black holes bend light rays, so they produce a characteristic shape associated to the bending of light. So Jean-Pierre Luminet in the 70s drawn the expected image of a black hole pixel by pixel by hand. So every dot that you see here is a pencil applied upon the screen to produce where its photon hit our screen. And this is the expected image. Now, this is a very well drawn simulation of what a black hole should look like, numerical, with model techniques. As you can see, these and these are very similar. And this is what we observe in the bottom row here. Okay, this was the discovery of N87. This was in 2019. It's a core of the N87 galaxy. Okay, so you only see a blurred image. Why is this? The resolution is not enough. So this was measured by the Event Horizon Telescope, which is actually a combination of different telescopes that work in unison in order to produce an image. So at the moment, we cannot resolve this image. This is blurred. We would like to resolve this image to see if actually this resembles it. But as you can see, as we were discussing in the section about photon spheres, we are expecting a central dark region, which is here, okay, surrounded by a luminous ring associated to this extreme bending of light. So this is consistent with this. Okay, at least quantitatively consistent. Because technology progresses in some future time, the community expects not only qualitatively consistent, but quantitatively. Or maybe not. Maybe this observation will not be exactly the theoretical expectation, meaning that there is something more in nature beyond the existence of black holes as described by general relativity. Again, this is science. So we could find something which does not conform to our initial expectations. So something that we shall see in the future. Now, there are several black hole mysteries, things we are not sure about. There are several inconsistencies in black holes as described by general relativity. We talked about a little bit about the existence of singularities. A singularity is a region in the center of a black hole in which general relativity can no longer predict. It's a failure of the theory to enact predictions about the fate of some observers when they get close enough to the center of a black hole. But there are other mysteries. One of these is the evaporation of a black hole. I was saying before that a black hole is something that takes everything that is that gets to a horizon. It never releases it back. Everything that crosses the event horizon never comes back. But this is a classical statement. But there is a class of theories which are called quantum theories, so quantum mechanics, which is a fundamental theory of the universe, already validated by evidence. Around 100 years ago, it's a kind of theory that it makes many different tools and machines that we have nowadays to work. Okay, so it's a very well-tested theory. What happens if we try to combine general relativity with quantum mechanics? In particular, what happens if we combine quantum mechanics with a black hole near the event horizon? This is something that Stephen Hawking did in 1973, and the reason why he became so popular. He considered the process of quantum pair creation as dictated by quantum mechanics near the event horizon of a black hole. And he got to the striking result that black holes actually emit radiation. So they are not completely black. They emit some amount of radiation. Now, this amount of radiation is extremely tiny for a stellar mass black hole and even more for a supermassive black hole. For instance, see, if this black hole emits radiation, and if this black hole were completely isolated, it means that drop by drop of radiation emitted by the black hole, eventually the black hole will deplete itself of material, so it will evaporate. But how long does this process take? So a black hole of one solar mass requires this number of times the current age of the universe, which I remember you that is about around 30,000 million years, okay, to operate. Okay, so it's extremely slow. But from a theoretical perspective, it's extremely interesting because it means that black holes are not really dark, or at least not completely, which is very exciting. At the same time, it's a problem. Why is this? This is called the information problem. Black holes evaporate. Now, this evaporation is completely thermal. This means that there is no information you can recover from this emission from the black hole. This emission tells you nothing about what is inside the black hole or the properties of the material that created the black hole in the first place, or that were absorbed by the black hole afterwards, information. Now, this cannot be, because the black hole contains information in a quantum system, in a quantum way, or a quantum mechanism. Now, quantum mechanically speaking, there is a precise meaning to the word information. And one of the main tenets of quantum mechanics is that information cannot be lost. But Hawking's radiation means that the black hole will evaporate, removing every sort of information about the material that created the black hole came into its course. This is a fundamental compatibility between our two most reliable descriptions of nature. Okay, so this is another motivation to explore the existence of physics beyond what that our current theories of the universe predict. Related to this, there has been proposed, and this is very interesting from a science fiction point of view, the idea of wormholes. This is a cousin of the black hole. It might have in a horizon or not, maybe not, depends on the family of wormholes, but they have a fundamental difference. The innermost part of a black hole is no longer a singularity. Instead, there is a finite-sized region, which is usually called the throat, that allows the transit of particles and light across of it from one side of the universe to another. So this is an idea that has been around for decades in the community. So this has been taken seriously for decades. We have no evidence of their existence yet, but again, this is science. We don't know. It may happen. So it's worth exploring it. They have some issues or some things that we don't understand. At this stage, one should recall that also with black holes, for 40 years after their proposal, there were things on black holes we didn't understand, and because of this, the community of its time thought that these objects, black holes, were theoretical constructs, no physical objects. So maybe the same thing is happening here. And just to conclude my talk, I'm going to show you a movie of the one movie I think it depicts the best the process of what will happen if someone try to enter into a black hole, but replacing the innermost part of the black hole, not by the singularity, but by a wormhole. So this is from the movie Interstellar. So if you haven't seen this before, so I think it's good to watch the specific clip of the movie that I bring you here, and then we are going to see something which is very accurate to the theory, the reality of what will happen if you approach a black hole, at least as we theoreticians understand now that black holes exist. So we're going to see it. So they are going to try to enter into Gargantua, not into into this black hole. Gargantua appears later in the movie. So this is a wormhole. So as you are seeing here, so the light trajectories, you are seeing how the wormhole is bending light. Okay, so they are talking about whether they will make it or not, because supposedly someone came before and crossed it. So you see the bending of light, and then this spaceship is entering the ergosphere. Remember, ergosphere, surface of co-rotation with the black hole. That's why they don't go in a straight line to the wormhole. They still circulate it about it. Okay, so they say the trajectory. So this is the sky stars. They are emitting light, distorted because of the gravitational field of the black hole, and they are getting closer and closer to the black hole or wormhole, whatever it is, closer and closer, co-rotating with it. Okay. So because this wormhole is supposedly a connection between two different universes, they want to travel to save mankind or no, or abandon it, and then they are going to cross the surface that separates the one universe from the other. Okay. At this point, the movie ceases to be completely scientific; it's more science fiction, and they are traveling through what is called a depiction of what will be the throat of the wormhole. Okay, so the movie is very interesting. I highly recommended it to see it. And just to finish my talk, so this is the current collection of the black holes that we are aware of. So all the blue dots that you are seeing here are mergers of black holes. So detected by gravitational waves. So you see two black holes here, from this one and this one, these masses. This is a scale of solar masses that merge in order to form this thing. Okay, and then there are black holes that have been detected by X-ray observations, like this one. And then there should be another black holes, which is the one in 87 I was talking about, and the other one at the center of our galaxy, which is in the constellation of Sagittarius stars. And just to acknowledge my host university, the funding sources, and the Brazilian community, the one that has been supporting me while I was there as a postdoc, and the Brazilian community that invited me to give this talk that I think I hope it will have been interesting to those of you that are spending 55 minutes of your time in order to pay attention to this. So thank you very much for your attention.
Thank you, Professor, for your presentation. Tarcísio now stop recording. And I think I